Now it will work, yeah. So I will be speaking about natural numbers in philosophy and of mathematics and in cognitive science. So I should underline that this research has been supported by a Marie Curie fellowship called Numbers, which just finished. We are now writing down the results from this experience. So I'm going to try to present you a big picture of what is happening in the two fields being philosophy of arithmetic and cognitive science. And my main motivation, so my question that I was looking an answer to was how to make a good use of cognitive science in psychology and how to use philosophy in cognitive science. Because I think that we can when you read papers of philosophers of mathematics interested in natural numbers, or you read all those people doing number cognition, you realize that questions that they ask or that we ask are like similar, right? The questions will be what natural number is, or what natural numbers are, if you want to stand on more like structuralist position, right? And the way the two fields interact seems to me, and still seems to me, insufficient, and I think that it will be very good for the two fields to find like a common ground and to exchange knowledge in order to, advance in understanding the concept of number. Of course, it is not, as you are going to say probably, it is not that obvious, because making even a possibility of approaching those two fields, I commit myself, when I try to like connect those two fields, I somehow commit myself to, I wouldn't say realistic view, right, but I have to at least think that there is somehow the common object of studies, right? And people would say, oh no, it's not the case, don't even try, no way, mathematicians and psychologists, they study two different things, there's nothing in common, right? But then my project will be fruitful as well, because then through analysis of concepts used in the two fields, I might come to the conclusion that concepts are used in so distinct ways that there is no possibility of connecting the two. But it is far from being shown or proven. So anyway, I will not be giving you any concrete answers, right? I will not be standing here saying, this concept of number from cognitive scientists, this should be used in basis and foundations of arithmetic because that's the one, that's the correct one. I will not do this kind of things, right? I will be much more moderate. I will first start by going through a very quick literature overview to show you what happens. And then, as I said, I'm going to show you this big picture where I'm going to speak quite a lot about how cognitive scientists understand their research, how they understand the concept of number. And if I have time, I will go to some consequences or explicative power of this paradigm. Right? Because which might be as well very important to say, and I will probably repeat it later in this talk as well. I will be presenting you one of the available paradigm on the market of cognitive science. Because as in philosophy there are different schools which might be competing. It's the same in the field of cognitive science or developmental cognitive science. People would disagree on the question what numbers really are. So I will be presenting one of the main paradigms which are now available at the market. Good, so motivations. As you know, and it's like quite a natural starting point, Frege in Grundlagen, he formulated an argument against psychologists, right? So one of the questions I'm asking, or I'm trying to find a reply to, is to see whether this argument will still hold for this research in cognitive science as known today. So what was the Frege's argument about? So he blamed psychology for lack of cooperation between philosophy of mathematics. He says in Grundlagen, you know, we would like to have those two collaborating because they are very close, but they cannot be close because in philosophy there's a lot of methods and mathematicians will never buy it, right? That's what he mainly says. So he blames psychology for this lack of communication or lack of cooperation between mathematics and philosophy. But we have to be very careful while saying it's just a rejection of psychology in general. Frege is pointing out at a very particular, very reductionist version of psychologism. He is speaking about motor phenomena or mental pictures, right? So where numbers are motor phenomena or mental pictures. And he says that when numbers are seen through this reduction, there is lack of objectivity, right? It is very subjective. He would say that when you, for example, think that natural numbers are mental pictures formed from the amalgamated traces of early sense impressions, it will prevent you from thinking about numbers in an objective way. And he says that we must remind ourselves, it seems, that the proposition no more ceases to be true when I cease to think, when I as a person, when I have, you know, I don't have those sensory impressions, when the sun ceases to exist, when I shut my eyes down, right? So otherwise, improving Pythagoras' theorem, we should be reduced to allowing for the phosphorus content of the human brain, right? And we don't want to do that. So in the psychological approach for Frege, there is too much of personal input, of subjectivity, and he does not want that at all. There is this very nice quotation, which I will read because it's here. I will not really comment on that. So what is known as the history of concepts is really a history either of our knowledge of concepts or the meaning of words. Often it is only after immense intellectual effort, which may have continued over centuries, that humanity at least succeeds in achieving knowledge of a concept in its pure form, right? So we want this objectivity of the pure form of thought. That's what we want to study. In stripping off the irrelevant accretion which veil in it form, which veil it from the eyes of mind. What then are we to say about those two? Instead of advancing this work, where it is not yet completed, despise it, and betaken themselves to the nursery, or bury themselves in the remotest conceivable periods of human evolution, there to discover, like John Stuart Mill, some gingerbread or people arithmetic, right? So we don't want to do that. We don't want to put anything from our own experience into mathematics, which should be objective. This is the attack of Frege on psychologism. And very surprisingly, and that was really something which motivated partially my further readings, is when I got interested in Frege's constraint, where Frege's constraint, as you might know, is a foundational principle formulated by Frege and then defended by neo-Fregians, which says that if you want to formulate foundations of a mathematical theory, you need to take into account applications of the elements of the intended model of this theory, right? So we have a theory, it describes class of models. One of those models is like better than the others, right? We can call it intended. And when you say, okay, this theory, actually, even if it has, you know, non-standard models, right? It has this ability to somehow express the behavior of the elements of this intended or standard model, right? And it's extremely important. So, of course, when it comes to Frege, you know probably all that he was defining arithmetic with Hume's principle, right? Which states that where numbers are properties of concepts, right? These are like second order properties. So if you think about the concept fingers in my right hand, sorry, I don't distinguish left from right, so if ever I make this mistake, please forgive me. So the concept, I have a concept fingers in my right hand, right? So the number, which is a property of this concept, is 5, right? If I tell you concept of the fingers of my left hand, the property of this concept is 5. Since I'm able to put my fingers into one-to-one correspondence, right? Then Hume's principle tells me the number of my right hand fingers and the number of my left hand fingers is the same, right? So application for Frege, so this Frege constraint in this original version, it says that I can apply a concept to a concept, and it is what is a number. Its primary property or its primary role is to tell me how many elements fall under this concept. But very surprisingly, Wright, who writes about Frege's constraint, and this discussion, it took place in 2000 in Notre Dame Journal. Shapiro, Bob Hale, they were discussing the problem of application of Frege's constraint for real numbers. So of course I will not go into this discussion because it's unrelated to my talk today. But I think it was, I mean, for me it was very interesting that when Wright himself, here's a quotation from his paper, when he says, oh, natural numbers, you know, reals, maybe Frege constraint applies, maybe not. Maybe abstraction principle for reals should be formulated following Frege's constraint or not. But numbers, natural numbers, for sure. I mean, it's like obvious. It's like, there's no doubt. It's cardinality constraint, right? And Hume principle, it captures this constraint extremely well. And then he says why. And this is the surprising quotation that I'm going to show you. He says that it seems clear that one kind of access to, for example, simple truths of arithmetic precisely proceeds through their applications. Someone can, and our children surely typically do, first learn the concepts of elementary arithmetic by grounding in their simple empirical applications, and then, on the basis of understanding thereby acquired, advance to an a priori recognition of simple arithmetical truth. I say a priori because I see no reason to deny that a child who reasons on her fingers or with a diagram, so diagram, I will not go into diagram, it's not very intuitive, but I mean, it works, right? 4 plus 3 equals 7. So, yeah. Has indeed acquired a piece of knowledge a priori in much the same way that the general geometrical intuition can be facilitated by means of a construction with paper and pencil. But if that is right, then there is a kind of an a priori mathematical knowledge which flows from an antecedent understanding of the way that arithmetical concepts are applied. It is not that pure knowledge comes first as apprehension of an a priori truth about structures, with the applicability of the knowledge so acquired, only drawing on one another has grasped how certain empirical situations can be viewed as, in effect, modeling aspects of that structure. Rather, the content of the a priori knowledge in question already configures concepts drawn directly from the applications. So, I mean, for me, it was extremely surprising to see that an application, even in a neo-Freudian account, even neo-Freudian searches for an application from the field of cognitive science. And the way in which it is done, and this is an objection, so I will not be, I'm very bad with reading quotations. I mean, I have not been trained as historian or someone who is like, you know, have this ability to read quotations. I think if they are here, I need to read them, but it's always a mess. So I will just, you know, wave and tell you the story of other examples. So for example, Stuart Shapiro, when he presents a competitive view of foundations of arithmetic, which is structuralist foundation, right? So the idea is that, so probably a lot of you know, the idea is that when you think about the structure of mathematical objects, you don't think about individuals, as it is possible in neo-Freudian approach, but you think about the structure, right? And it's like a structure comes first, and after your elements, they are somehow like placeholders, right? So the property of 2 in a structure of natural numbers, which is my favorite one, is the fact that it is like at this place and it is related to this number in this way and to this number in that way and to this number in this way, right? So the fact that at the place 2 there is a cow, it's like secondary property of this number, right? Or Julius Caesar, right? At the place of 5. He can be sitting there, but we don't mind. It can be whoever, whatever, because what describes numbers or elements of the structure is their properties. And Shapiro would say very freely and very frequently that his approach is actually supported by psychological research of pattern recognition, because humans are known to have ability to recognize patterns. And then, so again, another very arbitrary example to support an epistemology, right? Exactly the same situation as here. Penelope Maddy, she will do the same while justifying axioms for set theory, right? She will be searching, she will be providing some experiences known from psychology to say, yeah, my epistemological point of view is a correct one, C. And I thought it was like methodologically very doubtful and that one should not do this kind of moves. And then I thought that going from the other directions, so go to talk to psychologists, read what they write, talk to them, look at how they work, and try to understand what is going on in psychology, might maybe give us some way of constructing psychological or cognitive science support for one's epistemology. So that was my motivation. And those quotations from big names in philosophy of mathematics motivated me to do that. Then I started to search on the other side, right? So I started to read psychologists. And there's this book which is very influential and very good by Susan Curry. Susan Curry, she's a professor at Harvard, and she is very close for various reasons with researchers from MIT. Right, so Ned Block, Fodor, all this tradition, Pelishin, all this tradition, she's very well aware of that, and she has written a book where she explains, so Origin of Concepts, it appeared with Oxford University Press several years ago. And she claims in this, so in this book she formulates theses about how people learn concepts, and she speaks about foundations, like innate foundations, pre-verbal foundations for concepts creation. But what I wanted to, so I will be talking about Susan Carey paradigm quite a lot later on, because she's one of the people whom I studied and whom research I know. But here I just wanted to read you a very quick quotation, this time from her book. She says that my goal here is to demonstrate that the disciplines of cognitive science now have the empirical and theoretical tools to turn age-old philosophical dilemmas into relatively straightforward scientific problems. I shall illustrate the progress science has made in resolving debates about the existence, nature, content, and format of innate knowledge. I consider the thesis that conceptual resources are continuous throughout the lifespan, But what was very interesting for me, that she was standing on very explicitly on this very reductionist empirical position, saying like everybody will now have to come to some point, to some extent, to check what we are doing, right? Because otherwise philosophy cannot advance. And the very same position you will find in a book of Stanislas Dehaene. He is known, for example, for his book called Number Sense, right? That's the title of the book. The book is entitled in English Number Sense, and it has been published again 2 years ago, 2011. And again, Dehaene. He will be claiming that his research, which is just not only developmental psychology, but mostly neuroscience, he will be claiming that philosophy can be very strongly reduced to what they are doing. So, of course, as a philosopher, I will never agree to this kind of approach. And I proposed to, so in my project I was proposing to reconsider a little bit and to see what actually can be done. Good. So my big picture, which I'm trying to draw, it consists of two arrows. There is this arrow which is like ontogenetic concept development. And this one I'm going to comment on quite a lot. But there's another arrow which is very important, which I called historical concept development. I think I can I? No, I have no zoom to that. But here, so I will not be really commenting very much here, but as you can, maybe I should tell you what I mean by the golden N. So it is nothing very formal, right? Don't tell me, oh, N, but you know, if you describe it in first order logic, you will always have non-standard models. No, I'm just like, there's like no logic related to that. Like imagine something impossible. Everything we know about numbers, formal, informal, quasi-formal, it is like the knowledge that we have about those numbers. And this is maybe my weak point, that I assume such a thing existing, right? But I somehow, in order to keep this project going, adopt a kind of like working mathematician Platonism, right? Think about it like I'm a working mathematician Platonist, so I don't really have a very very formal explication how my Platonism behaves. It's just that if you think about like all different things that we can know about numbers, from, I don't know, studies of axiomatic systems of arithmetic, through developmental psychology, to, I don't know, set theory or algorithms, it is somewhere there, right? So we are learning about what numbers are, and very surprisingly, so here, I don't have a zoom on this little letters here, but I can read them. So I think that the nice way of going, I will not do that today, but I have written about it a little bit, is the idea defended by Shapiro, Stuart Shapiro, who, following Weizmann, thinks that concept of number is not open texture anymore. So the idea of open texture is that you have those concepts which like gain information from different resources, and their meaning develop, right? Like if you think I will be speaking about Quine, if you have like a web of knowledge, it's still like moving. And Shapiro, following Weizmann, he says, but yeah, this point, at this stage of our knowledge, it's not moving anymore, right? We just know about natural numbers everything we could know. Like there is like not like the meaning is now we got it. So Shapiro claims that concepts like natural numbers and concepts related, for me very related concept of computability, are not open texture anymore. Right, and I think it's a very nice way of looking at this axe or at this arrow, but I will not do that in this talk today. What I'm going to do, I'm going to concentrate on this ontogenetic concept development. And I'm going to tell you a story, or at least what I know from the story, what are natural numbers according to developmental cognitive scientists, right? So it's so those people work with children. It can be very small children, like infants, 4 months old, very small ones, or up to, I would say, like preschool children, right? 5, 6 years. Probably that's where it stops. Why? Because at age of 5, most of children, like well, healthy, undisturbed children, they will grasp something what they call the concept of number, right? I will explain you what the concept of number is according to those psychologists. And it is very important that it is not about like developmental psychology. This cognitive aspect is very strongly underlined because the motivation for this research is to understand how humans create concepts, right? So they will believe that every concept, and I have a movie, so I don't have a, you won't hear what people are saying, but you will see it, and it's very short movie that I'm going to show you if it works. If not, I will just tell you. But that's a very important part of the picture. The picture on which humans are supposed to have an innate knowledge, right? So we have a knowledge of which is inborn, which is preverbal, and which lies under or like comes first before the language develops, and the language will be developing in relation to this innate knowledge. They call it core cognition or core concepts. Core cognition, hypothesis about existence of an innate cognitive systems which enables humans to apprehend quantities in this case. And no, sorry, just need to find my. So how does it work for mathematics, right? So we're coming back to mathematics, and what is important, Karen Wynne, she's one of the person who did a lot of very interesting and very important research on number cognition. I will going to tell you about one of her experiments. I didn't found any movie to show you the experiment, but I'm pretty good with hand waving, so you're going to understand what was showing. So when it comes to number, cognitive scientists, they believe that there are two core cognitive concepts, two core cognitive systems that are related to quantity. First one is called parallel individuation, and it is not domain specific, which means that it will help children to develop the concept, or children or adult or human, to develop the concept of number, of quantity, but it is not designed, or it is not in our brain only for this reason, right? I'm going to say some words more about this module in a moment. Now I'll just tell you that there is another system of core cognition called approximative number system, which is domain related. So it will do only quantities. It is only about quantities, and it allows people to approximate numbers. I will tell a little bit more about it later. So parallel individuation. So parallel individuation works for numbers such as 1, 2, 3, 4. When it comes to 5, we kind of switch to, we can not really use this model to like understand or to apprehend what is 5. It means that we are able, from the first glance, immediately, account for cardinalities from 1 to 4, right? It is related to the idea that that our memory, like working memory, has constraints, and that, for example, people are able to track in a space up to 3 and maybe up to 4 elements simultaneously. There are like, so in this parallel individuation, there are like several, so this ability to track elements in a space is one of the properties of this module, but there are others. For example, a very important base for this model is something which is called Spelke object. Elizabeth Spelke, she's one of the researchers in cognitive developmental psychology, and in the 80s, 90s, she defined something which is called Spelke object. And the idea is that certain inputs from the outside, from the external world, are perceived as objects, right? They somehow forced children or forced adults to perceive objects as objects, right? To know that this is an object and this is not an object, right? And she says that, so there are several properties that children manifest sensitivity to violation of these features, and it's already at 4 months old. So these are like babies that cannot really speak, right? They are really small, but they will be already reacting to, so we can already measure their reaction to the environment. And we will observe that certain inputs from the external world, they characterize by cohesion, so that those inputs move as unified wholes, right? So it will not spread in a moment and then become many objects, right? So if something is an object for a baby, it's something which will be moving. It will be moving as a unified whole. There will be a principle of solidity. So, for example, that 2 objects cannot be occupy the same space in the same time. If 2 distinct objects move together, they need to be somehow connected. That's an observation as well that they are going to do. They will see that if they are unsupported, they will fall. So I will not risk my pointer, but you know what I mean. They will realize as well that, for example, there's this very nice experiment. And so, sorry, I don't have any picture that I could show you, but I can tell you the story of the experiment. So the experiment, so you have a baby, right? 4 months old, very small child. They measure attention span, so how long the child is watching. If a child watches for a small period, means child is uninterested, right? The other way of measuring is the frequency of sucking, which can be measured, and we can see, and so it is observed that children which suck more frequently, they are more interested in the situation which takes place, which means situation is not habitual, right? They are not used to the situation. So the experiment looks like follows. So there's a child. She or he looks at the, you have seen those little theater, and in this theater, the child sees an object. And then there is an ekran, something here, and then it goes up, right? Everything goes fine. And then one group can see that the ekran goes down and then stops, right? Normal, there was something there. But the second group can see, that, so they can see this object, they can see that object is hidden, and then for some reason, it goes down, no object. So it's surprising. So a child will show a surprise, will be looking more like longer, or will be sucking more frequently. So this kind of experiments are done to confirm or to show that there are like objects, right? And these features, claims Pelke and other people defending this paradigm, are innate and they are independent of the experience, right? So they are pre-verbal for sure. A very interesting experiment related to this parallel individuation system has been done by Karen Wynne, so the lady that you have seen with the other experiment a moment ago, which was about subtraction and addition abilities for children of 8 months old. So it is 1992, Nature, one of the most discussed cases in the field, and what the experiment was about. So imagine you have a little theater, right? And there is a little ecran that will go up and down. Good. There are 2 puppets. Imagine these are puppets. So a child is sitting, or children, there is one object here, children see the object. Then the ecran goes up, and then children see a hand coming here. They can see this. It holds another puppet. It comes here, and then the ecran goes down. Surprise! There's just one object. And then frequency of sucking goes up, right? So surprising. The control group will have no surprise. They will see 2 puppets. And so there was a variation on this experiment. Some of them were like the hand was putting the puppet behind the screen, or there were 2 puppets and the hand was taking away one of the puppets. And so children behave as predicted by the principles of addition and subtraction. So Karen Wynne, she took the conclusion from the experiment, the original conclusion, was that children already at very young age are able to do some very simple arithmetical operations. So of course there was like a lot of noise, a lot of criticism. The idea that it's not about addition and subtraction, but only about one object and a Pelke bundle, it's enough to explain what happened, etc., etc. So I will not go through this discussion. I'm talking about this experiment just to give you a feeling which kind of experiments are done to show that there is this parallel individuation system which allows us, which sensibilizes people to small quantities. Good. So this set-based quantification, so what happens for 3 or 4, so evidence show that babies, but as well adults, they can track up to three similar objects in the field. So if you have 3 children, if you go to a playground and you want to have time to read your book, dress them similarly, right? All dressed in yellow, you can just be sitting and looking at them and be able to see them simultaneously moving in the playground, right? If you have 4 children, don't dress them all in yellow because you will lose one. I mean, there is a possibility. Dress 2, or at least you will have to pay attention, right? You won't be reading, you will not lose a child, but you will not be reading your book, right? So dress them in red and in blue, right? And then your cognitive abilities let you track up to 4, 2 by 2 distinguished objects in a field, right? And there's a lot of experiments done, done with that. And it is again, by cognitive scientists, related to the system of parallel individuation. Good. So before I continue to speak about those core concepts, and all those happens before you learn any language, right? So you have an access to those abilities before you know the names for numbers, or maybe you know the names for numbers, but you cannot relate them to cardinalities, and I'm going to talk about it in a moment. So the second system is called approximate number system, or ANS, and it lets you approximate the number of people, objects, dots, leaves, bird nests, whatever, in a space, right? So it is not only for visual input, it's modality independent. So it is shown that it works as well for the repeating noises, for touching. Okay, so it lets you approximate pretty quickly, but inexactly. And the curve goes as follows. For small numbers, you can approximate quickly and rather like exactly. For bigger numbers, it is more and more difficult. So it works in the following way. So I'm coming in this room, and even if I don't want to count you, my brain does it for me, and somehow I immediately, even unconsciously, have a brain activity which is related to me approximating like 20 people in the room. Right, so I get in, and before I even said or even wanted to tell you there's 20 people in the room, I had already a brain activity which was sensible to the quantity of people in this room. Apparently it goes, so I'm just still in the process of understanding all those processes. So if I don't go into details, it might mean that that there are certain things which are still not unclear to me. This system of approximate numbers has the following property. It allows you, for example, so we share it with animals, right? This is a very interesting thing about it as well, because as animals, we need the system to survive, to, for example, compare where there is more food, right? And to direct ourselves towards this direction. It works in so it will be working with ratios, like the difference, so comparing two sets, it's much easier when the ratio is bigger, right? So what does it mean? It means that, for example, comparing 10 and 20, saying that here it's more than here, so that 20 is more than 10, it's as difficult or as simple as comparing 20 and 40, and it's easier than comparing 20 and 30. Right? Because it's about the ratio between the elements of two sets. It is not about the difference between the two sets, like the difference in number of elements. Another thing which is interesting about this is that, so it is shown, and since I have 15 minutes, I will maybe speak about it immediately instead of speaking about it later. There is an evidence that there are tribes which has not developed names for numbers, which has developed the names only for 1, 2, 3, 4, 5, and after is many. And then those people, when you ask them how a number line looks like, they will not be using the number line that we use, which goes like this, right? So you have like the same distances here, like linear number line. They will be using a logarithmic number line, right? So 1 will be here, 2 will be somewhere here, 3 will be somewhere here, sorry, it's like approximative, right? And after, like, the others will be there. And this observation has been done as well with children who has not learned names for numbers and the number line and the successor principle yet. They will have a tendency to represent numbers on a logarithmic scale instead of the number line, the linear scale. And it is very interesting, and it is claimed that it is related to this ANS, because when you think about how ANS works, for example, for 1, it is very exact. For 2, 3 as well. When you come to 5, when you approximate 5, if you are not well trained, you will have, like, you know, between 5 and 6, right? For 6, this space is bigger, right? The approximation takes more. So after, when you go to 100, approximating 100 means you go from example 92 to 108, right? So it gets flatter and flatter, bigger and bigger, right? And it corresponds to this logarithmic scale. So Dehaene, he claims that there is a very strong correspondence between the two, right? And we have a psychological evidence for this logarithmic scale for approximate number system. Good. So we have those two models, right? But, right, says cognitive scientists, there is no exact numbers, right? The fact that I can tell you there is about 20 does not mean that there is 20, right? So where are the exact numbers that mathematicians are going to study, that philosophers will be interested in? Where do they come from? So they say that what is necessary, we need number words and counting routine, right? So maybe what is interesting for us now is that I'm going to tell you about which kind of, maybe I will first tell you about one experiment more. That's this one. So what has been observed? It has been observed by an experiment called Give N, that children learn names for numbers successful, right? So like in a succession. Right? So children which understood the concept of 2 has already understood the concept of 1, right? If a child understands 4, means that this child already got 1, 2, 3, and 4, right? It is not like you cannot understand what 4 means before you have understood what precedes. It is shown that when you got to 5, you are so-called cardinality knower, which means that you are able, you kind of grasp the successor, that putting 1 more gives you 1 bigger number. So once more, what happens? Children know names for numbers very early because we sing to them songs, because we count with them, because they can hear that in a space, in a family, at school, whenever. So they know names, but it forms kind of like a placeholder structure. They don't understand the words, right? The experiment, Give N, consists in having like a puppet, like a teddy bear or something, and then the child is said, "Oh, could you give 2 to the teddy bear?" And then a child gives a bunch, right? "Oh, are you sure it's 2?" And then the child can even count 1, 2, 3, 4, 5. "Oh, so can you give now to teddy bear 2? And the child puts more, right? It means, because it happens, right? So it means that the child has not grasped the concept of 2 yet, right? So they will say a child understood, thanks to this experiment and other experiments which are conducted, a child understood what is 2 when the child on a demand, "Could you give 2 oranges to Anteater?" A child gives 2 oranges to Anteater. "Could you give 5 oranges to Anteater?" A child will give 5 oranges to Anteater, 6, 7, 8, etc. Right? So it goes, it goes like this. So how much time do I have? Because I might adjust.
7 minutes.
Good. Okay. So from my philosophical perspective, so maybe I will now speak about this picture, to repeat a little bit once more how things go, and I will introduce the concept of bootstrapping, which is an extremely important concept in the moment where the language acquisition come to the picture. So from the one hand side, you have those core concepts, this core cognition, pre-verbal, automatic, not related to the language. Then you have language and placeholder structure, right? Whatever, a child learns names for numbers in the language of his or her parents. There are studies of multilingual children, whatever. So child has this ability, knows the names, and can somehow see that they are used for counting. This language is symbolic, so the representations for those, in addition to the representation for those, humans create symbolic representations for numbers. And now what happens? It's a bootstrapping. And bootstrapping is a concept introduced by Susan Carey, which is based on Quine idea. So Quine never uses the word bootstrapping. But Carey, she thinks that, she claims that it comes from word and object, where Quine says that when you have a web of knowledge, right, when the meaning of this word changes, like for you, because you got some additional information, then the whole structure moves and the meaning of other words kind of readjust, right? So it's like a holistic picture of how the meaning is acquired in the language. So here, it's like a simplified version of that, right? So this placeholder structure will be achieving information. The names will achieve meaning with this bootstrapping. So it's not like once a child could see that that the number 2 it relates to 2 apples, then it's 2. But another day a child will see that to 2 oranges as well, or to 2 beets, or to 2 something. The meaning of 2 will increase, like the understanding or a concept will gather the meaning for a person, but in the same time the whole structure will somehow acquire this meaning. And in particular, it will acquire the meaning of the successor, right? So the successor principle, the idea that if you add 1 to the set, it gives you the following number on your number line, right? In your placeholder structure. Good. So now I will unfortunately stop here. Fortunately or unfortunately, I just want to get back to the whole picture. So this framework and this constant tension between language acquisition, which is based on core cognition, is claimed to be a very explicative way, and it has a lot of, it provides a framework to explain, for example, what happens with those people who never, or those societies which never developed any recursive system for number names. It explains what happens, where the problems come for example, mistakes at school children, or it might be somehow used to explain things in philosophy of mathematics. Sorry, I'm just trying to be as much precise as I can, but I don't really have much more time. So thanks a lot.